So today I will deal with the interaction between diet and gene polymorphisms in the development of the metabolic syndrome. So as you may know, a central start point for metabolic syndrome is obesity, and especially visceral obesity, with a progression in the phenotype with insulin resistance, glucose imbalance, and dyslipidemia, then leading to the so-called metabolic syndrome. And this leads to an increased risk for developing type 2 diabetes and cardiovascular disease. So factors playing a key role are metabolic stress in general, and also inflammation. And two of the big stressors are known to be unbalanced diet on one hand and reduced physical activity on the other hand, because our genome has not been made for present life, but for prehistoric life with a huge physical activity. And of course, some individuals can have a sensitive genome, especially regarding these two aspects, and that could drive to the development of the metabolic syndrome. In fact, we have had several presentations today. Previous work indicated that sensitive genotypes only weakly predict obesity and type 2 diabetes development. On the other hand, only limited studies have shown a direct or causal link between dietary habits and the metabolic syndrome. So in that context, we developed research projects in order to determine the influence of dietary habits of gene polymorphisms on the development of the metabolic syndrome, or the risk factors associated with metabolic syndrome. So today I will refer especially to a recent prospective study, which is a nested case control study performed thanks to the Suvimax French cohort. This study has been performed in the framework of a European-founded FP6 project called Nutrition, and the activity participants were the lab of Serge Herberg in Paris, running the Suvimax cohort, the group of Hélène Roche in TCD, UCD in Dublin, Hitachi Europe, providing some tools, and finally my lab in Marseille, and we coordinated this study. So clearly our aim was to investigate the role played by the habitual dietary intake, especially fatty acid in the subject, some gene polymorphisms, and the incidence of the metabolic syndrome. Fortunately, we were able to use the French prospective Suvimax cohort, which started more than 10 years ago with 13,500 adults, which have been followed for 7 years. So the first piece of work was to make the selection of the metabolic syndrome cases, and they match controlled at the end of the follow-up. So the selection of cases was made based on the NTEP ATP3 criteria, at least 3 criteria among 5, which are elevated waist circumference, separately in the two sexes, blood glucose, blood pressure, blood triglyceride, and low blood HDL cholesterol. On this basis, we selected the cases and we matched the controls with absolutely no abnormality or isolated hypertension, and they were matched by gender and by age. So this resulted in a selection of 877 pairs of matched cases and control. So as you can see, I hope you see, on this slide, we have separated men and women, cases in red and controls in blue. Of course, for all the criteria involved in the definition of the metabolic syndrome, there was significant difference between cases in control in men and women for waist, systolic blood pressure, diastolic blood pressure, glycemia, HDL cholesterol, and triglyceride. But also for other parameters, we have measured BMI, insulin, C-peptide, non-esterified fatty acids, OMA and Quickie scores. Only for total cholesterol or LDL cholesterol in men, there were no difference. So the cases in the control have been carefully selected. So we observed that the med cases compared to the controls had overall a lower education level, were more frequently smokers, and were less physically active. At inclusion at year 0's cohort, we observed slight but significantly different daily energy and nutrient intake, as shown in this table. As you can see in the med cases, the total energy intake was a little bit smaller, but alcohol intake was higher, as well protein intake. Carbohydrate intake was slightly lower. Total fat and saturated fat were comparable. MUFA was intake was a little bit higher. PUFA intake was slightly higher. As for linoleic acid and arachidonic acid, and for no big difference for N-3 long-chain fatty acid. So some slight difference in dietary intakes in this subject. So then we determine the plasma fatty acid profile in all these subjects. So we have the med cases and the controls. And so to summarize the data we have observed in terms of percentage of each fatty acid over the total fatty acids, we found that in the cases there were higher level of myristic acid, no difference for palmitic, higher level of palmitoleic acid, lower level of stearic acid, lower level in oleic acid, lower level in linoleic acid, but higher level in gamma-linolenic acid, same level for alpha-linolenic acid, higher level for dihomo-gamma-linolenic acid, and for arachidonic acid. Small difference, but for N-3 fatty acid, with a slightly lower level in the cases for EPA, DPA, and DHA. And finally, when looking at the ratio for desaturases, we found that the ratio for delta 9 desaturase was higher in cases compared to control, with the two markers from palmitic and from stearic, and also the delta 6 desaturase index was higher in the cases, but the delta 5 desaturase index was lower. So as you may know, this relative concentration are not independent values. So in order to have a sound analysis of the data, we perform a principal component analysis to determine the uncorrelated factors from this plasma fatty acid analysis. And the PCR provided us 4 loading factors, explaining in total almost 80% of the variance. So the first factor was a combination of myristic acid, palmitic acid, so saturated fatty acid, with a high and a low level of linoleic acid. The second factor was made of high long-chain N-6 fatty acid, with a high value for this 3-1, and also combined by a high level of palmitoleic acid. The third factor was made of all 3 long-chain N-3 fatty acids. And factor 4 was a combination of low saturated fatty acid, especially stearic, but high oleic and high alpha-linolenic acid. So we use these 4 factors to determine, using multivariate regression analysis, the old ratio for having the metabolic syndrome 7 years later. So we have used an adjusted model, then a model adjusted for age, gender, dosage center, smoking status, and physical activity at entry, and also further adjustment on education level, BMI, and waist circumference. So on this slide, all subjects have been involved, and as you can see, the old ratio for getting the metabolic syndrome 7 years later is comprised between 1.6 to 1.4, depending on the different adjustment. The factor 2 also provided odd ratio in the range of 1.9 to 1.5, as well as a factor 4, or 1.5 to 1.4. In contrast, factor made with the high long chain N-3 buffer provide a low and reduced odd ratio comprised between 0.85 and to 0.8. But in fact, in this cohort at the entry, some subjects already had the metabolic syndrome. So we have made a second set of calculation by excluding the subject which already had the metabolic syndrome at baseline, at inclusion. And again, we found that factor 1, which is high long chain N-6 buffer plus palmitoleic acid, provide a high odd ratio for getting the metabolic syndrome from 1.7 basically to 1.6, depending on the different adjustment. This was basically the case, but with a slightly lower odd ratio, with factor 2, which is high SFA and low linoleic acid, from 1.2 to 1.2. And factor 4 showed also an odd ratio, a significant odd ratio above 1, but unless adjustment was made on baseline or waist circumference. Regarding the high long chain N-3 buffer factor, the significance of the reduction in the odd ratio was lost in this case. So the conclusion of this first part, dealing with plasma fatty acid, is that the metabolic syndrome can be predicted 7 years before by a specific plasma fatty acid pattern. Indeed, the factor high long chain N-6 buffer and palmitoleic acid was the strongest indicator. Indeed, it was the only one predicting the onset of the metabolic syndrome, both in men and women. And also the data obtained highlight the complementary role of fatty acid intakes, especially SFA and N-6 buffet, of saturated fat, fatty acid de novo synthesis, and also the endogenous interconversion, and especially through desaturases, especially 2 desaturases, delta-6 desaturases implicating linoleic acid, and further long-chain N-6 fatty acids, but also the delta-9 desaturase, which is involved in the desaturation of palmitic to palmitoleic acid, especially, or also steroic to oleic acid. So this suggests that the diet low in SFA and low in N-6 buffer, but high in N-3 buffer, could help in preventing the development of the metabolic syndrome. So the second part of our work was dedicated to gene polymorphisms. So we made an extensive search of literature. This was made in 2004 and 2005 using available database, and we selected 469 candidate genes of interest in the field of obesity, hypertension, insulin resistance, hyperglycemia, dyslipidemia, and inflammation. Because this number of genes was too much for us, we made a selection and identified a top gene list of 182 genes. Then through the database we look at SNPs, and especially at tag SNPs, and from the selection we made for SNPs with a frequency of above 5%, we identified 806 SNP to genotype. So genotyping was made from after a DNA extraction of the blood sample of the subject, and genotyping using especially Illumina technique, but also car bioscience for some SNPs. Sorry. So that's the list of the SNP we used. Of course, we have no time to go into details. Some are missing. For instance, FTO is missing because it was discovered 2 years later when we start. So the first analysis was made using the Fisherman test for allele frequencies. And among the 800 SNPs tested, we found that about 50 SNPs were significantly different in cases in control with a moderate significance. But we found also that 14 SNPs in 13 different genes were found highly significant. And as you can see, with the symbol of the gene, these genes are in the field of lipid synthesis and metabolism. They are in the field of inflammation, in the field of metabolic regulation. Some provided an increased risk, some provided a reduced risk. So then we looked at the difference in terms of genotype frequency between cases and control. And we selected about 10 SNPs in 9 genes, which with a Fisher test were highly significant, but which lost significance after controlling for multiple tests. So using this strategy, only one SNP in ApoB resisted to this test with an old ratio for the metabolic syndrome of 1.56. So in fact, we would like to have a more global approach of this data. So we use a random forest, which is a classification tool, very robust, which is based on decision trees. So we use for this analysis 5,000 different classification trees to have a robust analysis. The first step in this analysis is to make a selection of variables from all the variables available. In fact, we started from the 806 SNPs, the 9 dietary fat variable, the 17 plasma fatty acid variables, the smoking status, the physical activity, the education level, and the gender. And random forest, selected forest, the key variable. These are 3 genetic variables, the SNP in ApoB, 1 SNP in ACB, and 1 SNP in LTA, 2 dietary fat variables, saturated fat and linolenic acid, 10 plasma fatty acid variables, and physical activity. Based on these selected variables, random forest were able to classify with a rate of 70% the metabolic syndrome cases versus the control, which was a rather good rate. If you look at the importance of the selected variable by random forest, we found first that dietary variable play a role, but not a key role. That plasma fatty acid, in terms of number, but also in terms of amplitude, play a really key role, and palmitoleic acid having the most important key role in this aspect, and also some desaturated fatty acids. And finally, looking at the 3 genetic polymorphisms, their importance was rather moderate. So I think there are some links with some presentation we have had today. So in fact, we try to look more carefully at the interaction between some gene polymorphisms and the plasma fatty acid, because we thought that maybe it could be very informative. And in fact, that's what we found. We'll give you today 3 examples of recently published papers on this aspect. So first we look to a SNP in the adiponectin receptor 1, and we look at the interaction with fatty acid on the HOMA index in the metabolic syndrome cases. So as you can see, we segregated the subject with AA minor allele and the heterozygote and the GG major allele. And we also dichotomized the subject with in black a low plasma SFA level, and in white with a high plasma SFA level. And as you can see, within individuals with a plasma SFA concentration above the median, the minor allele homozygotes have significantly higher HOMA index than both the heterozygotes and the major allele homozygotes. This clearly illustrates an interaction between this allele and the level of plasma saturated fatty acid. And what is especially interesting is that this finding has been replicated in another cohort of cases with a metabolic syndrome, which was made of more than 400 metabolic syndrome cases. Second example comes from the leptin receptor gene. We look at 10 SNPs in these genes. Only one was associated with the metabolic syndrome, and primarily in males. As you can see, the GG homozygotes had a greater metabolic syndrome risk related to the minor ELR carriers with a node ratio of 1.65. And it was especially in male. Also, we made some dichotomization depending on the level of the various fatty acids in the plasma. And what we found is that as compared to the median, the subject with a low N-3 status here, or with a high N-6 PUFA status here, exacerbated the genetic risk conferred by the GG homozygote on insulin resistance, not shown, but on metabolic syndrome risk. This is this table. And on the contrary, this association was not found in the subject with either high N-3 fatty acid status or a low N-6 fatty acid status. Also, this observation has been replicated in the other metabolic syndrome cohort, where we show that we also found a lowering in the insulin resistance after 3 months intervention diet, with a diet containing and rich in N-3 PUFA. As you can see here, there was no change depending on the allele and after 3 months with a low-fat, high-carbohydrate diet. But after the same diet, but enriched with N-3 PUFA, as we showed here, there was a significant change in the GG carriers upon the intervention. So the third example illustrates another strategy we developed, which was to sum the effect of different SNPs. So we selected 3 genes implicated in inflammation, IL-6, LTA, and TNF-alpha genes. And we looked at some SNPs. So we found that in LTA genes, that the minor A allele carriers, and in TNF-alpha carriers, the major G allele homozygotes, have increased metabolic syndrome risk with odds ratio of 1.37 and 1.35. In this subject, if they also carry the IL-6 GG genotype at a given RS, it's further increased the risk of metabolic syndrome up to an odds ratio of 2.1. But also, it significantly increased the risk for abdominal obesity, hypertriglyceridemia, and hypertension. And also, if we dichotomize the subject regarding the PUFA to SFA status in the plasma, this association with the three some genes, SNPs, is markedly strengthened when the subject has a low PUFA to SFA status with an odds ratio as high as 4.4.
5 minutes.
Yeah, 5 minutes almost. Okay, so during this case control study, we also found interaction between different genes and the fatty acid status regarding the metabolic syndrome. Just to briefly, with C3 gene and polyunsaturated fatty acid, with STAT3 polymorphisms and saturated fats, with ACSL1 gene and dietary fats, fatty acid, with ACC2 gene polymorphisms and dietary fat, especially N-6 polyunsaturated fats, in the TCF7L2 locus, in interaction with dietary saturated fat, and finally with SNPs in ApoA1 and ApoB, which are in interaction with fatty acid to induce a risk of metabolic syndrome. So just to conclude, we found that the onset of the metabolic syndrome is associated with dietary lipid intakes as reflected by the plasma fatty acid. This was the case for saturated fatty acid and for N-6 long chain PUFAs. And also we found that N-3 long chain PUFAs reduce the risk. We identified few gene polymorphisms involving energy metabolism, lipid metabolism, or inflammation that can make subjects more susceptible to develop the metabolic syndrome. But more importantly, we found that the interaction between fatty acid status and gene polymorphisms mainly predict the metabolic syndrome. Of course, further studies are needed on much bigger population and using sophisticated analysis tools to make definitive conclusions. So we saw that this piece of data we obtained during this study supports a concept we collectively suggested in the framework of the European Nutrigenomics organization, that in present time we can state that nutrition is essentially a gene-environment interaction science. And my personal point of view regarding personalized nutrition is that, of course, it should be a worthwhile achievement in the future, but that much more scientific knowledge is needed, as well as ethical consideration. So I would like to thank my collaborators, especially Louisa Goumini, Serge Herberg, Fabien Zabot in Marseille, and Richard Planel, who coordinated with me this study, and also, of course, a great contribution of Hélène Roche and Catherine Phillips in Dublin. And I thank you for your attention.